Hello, I'm Channa Bankapur. I'm a trainer at GoMaster.in. So today's problem in September LeetCoding challenge is out about 4 hours back, and here is my solution. So the problem is evaluate division. So as part of the input, it has a bunch of equations, and all equations are given in this format: a divided by equals to k, right? So if you just go with the example here, there is a divided by equals to 2, right? So that's given in this form, and a and b are given as strings, and 2 is given as a floating point number, right? A double data type. So that's input. So we have two of them here. A divided by b is 2.0, and b divided by c is 3.0, right? So that's what is given. And as part of the query, we have something like a by c, b by a, and so on. What does it mean is we want to find the value of a divided by c. If I know a by b and b by c, a by c is going to be just a product of these two, right? A by b times b by c is going to be a by c, right? Which is going to be 6 in this case. So that is what we need to find for each of them. B by a is just reciprocal of a by b, which is going to be 0.5. And if you take something like a by e, we don't even know what is e because that is not part of our system here. As part of the system, we only know the symbols or variables which are a, b, and c, right? We don't even know what is e, so we are going to return -1, indicating we don't know that. Let's look at fourth and fifth query. So fourth query is a by a. We know what is a here, as in we know there is a variable a. So a by a is going to be 1. So that's why we are returning 1 here. And we have x by x here, but we don't even know what is x. We are not going to speculate and say it is 1. Instead we're going to say it is -1 because we don't know that symbol, right? So that's how the question goes. And then we need to figure out how to find that. So if you see example 2, there the variable name can be like bc, and so it could be little longer than just one character. So you can just treat it as a string, right? That should solve the problem, right? And these vectors of an equation and values go hand in hand. That means equation of I and values of I put together is going to be one equation, like we have seen earlier, right? All right, so the output is expected again in double as a vector of each of these queries. So the output vector is going to be of the same size as queries vector. And they are expecting a real number. So if you use double as a data type, I think it's going to meet the criteria. So they expect you to do it in as in the output should be up to 10 power minus 6 precision. So all of that is going to be taken care. All right. So let's see. My first approach is something like this. To find, so there are some cases where if one of the symbols of, if my query is p by q, both p and if either p or q is not present in my system, I'm going to say a -1. If both of them are same, p and q are essentially same, I'm going to say 1, right? And if p and q is one of the equations given, then it is also straightforward in a way. But if both p and q are not there, like this in this example, a by c, both a and c are there in my system, but I don't have a direct equation for a by c. We need to derive that part. So how do we do that? And always all the queries are in the form p by q. And don't bother about solving these equations for a, b, c separately. Even though this is a set of equations representing one system, they say there is no contradiction there. That means it's a system. But you don't have to worry about finding that. Probably we won't be able to find ABC because at least in this example, there are only 2 equations and 3 variables. So we won't be able to solve that all the time. So don't bother about that. All we need to do is find these values, right? For the queries, which are again fractions, right? So my idea goes this way. So how do I represent this one? I can represent it as, for any symbol is essentially like a variable to me. So I can use a map with that as the key. But the value has to be a double value or something, right? But here I don't have a value for every variable. So say in this case, a by b equal to 2, a is essentially b times of 2.0, right? So, but this is somehow I need to represent something like this. So I ended up representing the same way. So I'm going to use a as the key, and this is the value for me. And value itself has two parts of that. One of the part is another variable, and then whatever the double value we have, right? The real number we have. So this is how I ended up representing that. So and then not just A by B, I'm going to, so for A by B, I'm going to represent. So in this example, let's see, how do I represent? So A is going to have B comma 2.0. So this represents A by B equals to 2.0. And when we have A by B, we also know B by A. So I'm going to represent B by A also, which is going to be a reciprocal of that 2.0. Now, how do I represent B by C? So B is already there as a list. So B by C is 3.0. So I'm going to have one more pair here, C comma 3.0, right? Similarly, C by B is going to be C at C. We have B comma reciprocal of 3 is going to be maybe 0.33, something like this, right? It's going to be a double type, so that you should take care. Now, this is what my representation looks like for the system here, right? These are equivalent. Now, to find A by C, what I'm going to do is, obviously those cases are going to be separated out. But now what I know is, in a typical case, both my symbols A and C are there in my system, but there is no one single equation which covers both, right? But if you see, A by C is essentially equal to what we have here, A by B and times B by C. A by B is present here, which is kind of represented here, right? And B by C is represented somewhere here, but they are in two different lists. But what we can see is B by A is also there. B by A is there in the same system. So if I find one system or one list where both my symbols are there, A and C, what does it mean is we have B by A and we have B by C. Now, if I divide B by C by B by A, what I'm going to get is A by C. Right? So that's all we need to do. I need to search for, suppose if P by Q is my query, I'm going to search for a list having both P and Q, which looks like this way. For example, if it is X, where P comma some K1 and Q comma K2 are the values. So then P by Q essentially for me is going to be this K2 divided by K1, right? That's all I need to do. And it kind of works for this scenario. And I try to work with this, and then it looked good. So for the examples given and couple more examples I generated, all of them worked nice. So here is my solution. I'm just going to explain that. At high level, I have a map here where string is the key, and then the value is another map having pairs of string and double, because for each of those uh, for each equations I need to have these bunch of pairs. I'm using map here again because searching needs to be faster. Otherwise, this is called key vals. This is the whole system now. And this for loop from line number 5 to 26 is going to build that data structure, which is the system in the representation I was explaining. So the first part here is going to basically insert A divided by B, right? If A by B is the equation, it's gonna just, for the list of A, it's gonna add this value called B by say K. And this second part is going to just do the reciprocal of that. For the list of B, it's going to add A divided by 1 by K, right? So this is what we do for every equation, right? So now once we have that, we need to construct the solution, and this is what I'm doing. So RES, short for the result, is is what we need to build. So I'm going to have, that is obviously has the same size as the queries vector. So I just resized it here itself. Now look at this. For each query, I'm going to generate or find the answer, which is going to be stored in RES of I, right? So what I need to do here is, there are few cases I want to take them out. One is, suppose if the query is say P by Q, if either P or Q is not present, then I'm going to say -1 and then update the value. That's all I need to do. Now, when I come down here, obviously both of them are present, but if both of them are same, they're identical, like A by A kind of thing. In that case, the answer is 1. So I'll update that and then get rid of that case. And this case is, if there is a P by Q equation in my system already, that means there is a list here where P is present and then Q and some K value is present. So I look for that, and directly I'm going to return K if it is already present, right? So that means if the question has A by B, and if they're asking for A by B as a query or even B by A as a query, I have a direct answer there because my system already has that. I'm going to return it. So these are trivial cases or the base cases. So here is what I'm going to handle for a little more generic case. What I did here is I went through each of the lists in my representation and look for both symbols of the query, right? This one and this one. If both of them are present in the same list, then as I explained in the earlier method, I'm going to just divide the second value divided by the first value. So that's going to be the result, and then I break out of this. It worked nicely, and actually it worked for all the cases I thought of. But yeah, to my surprise, it failed for a case, and then I realized, oh, there are these kinds of inputs. Look at this, what happened here. The input has x1 by x2, x2 by x3, x3 by x4, x4 by x5. All I knew was if I have two of these things, say x1 by x2 and x2 by x3, I can find x1 by x3. But they are asking for x1 by x5, right? That won't be possible with searching in a single list, right? It's more like a transitivity there, right? I need to have more values per list to handle such a thing, right? So this failed here, and then I realized that, oh, I need to handle this case. So now if you look back into this, that's when it looked like, okay, this is all about transitivity. That means there is some kind of path from x1 to x5. In that case, I'm going to just multiply all of these values, because look at this. What is x1 by x2 times x2 by x3 times x3 by x4, um, sorry, x4 times x4 by x5. If you look at here, this is essentially x1 by x5, and that's what the query is. So the answer for this one is going to be 3 into 4 into 5 into 6, which is 360. That's what they're expecting. So it's kind of a path. And now if you look back into the representation we used. So for a, or sorry, in this case x1, right? For x1, we were representing x2 comma say 3 in this case, and for x2 we were representing x1 comma reciprocal of 3 is going to be 0.33, something like this, right? Similarly, for x2 by x3, we had x2 had x3 comma the value of that is going to be, I think, 4, right? We had 4.0 there, right? So if you look at here, this representation is already what is called a graph representation, which is adjacency lists representation. So where you can think of these as nodes, and this is another node with a neighbor node, and this is the cost of that edge, right? So for every equation, for say in the form of a by b, we have a node called a and a node called b. So there is an edge from a to b, which is that k value, which is the value of the fraction, and b by a is going to be just the direction in or edge in the reverse direction, which is going to be 1 by k. So what we did in this data structure building stage is we built that adjacency list. For every equation, there are two edges. We added them to the list. So in a way, I am already constructing a graph, right? I just didn't realize that I was constructing a graph. Now, what we need to find here is if there is a path from, suppose if they're asking for say x1 by x5, I need to find if there is a path from x1 to x5. If there is a path, then I just have to multiply those edges, right? That's all I need to do. And that's what they mean by there is always an answer and you don't have to worry about invalid cases, right? So earlier what I did is I only considered up to one edge. I didn't even consider two edges. But in this example, they are expecting three edges. One edge here, two edge here, and three edge here. I don't even handle two edges in my code at the moment. So this is where I need to apply the paths, and it's not really hard actually if you think through, because I already have the graph representation, and I just have to figure out some kind of traversal in a graph. And if there is a path, I just have to multiply those edge costs, which is not too hard. So what I did is I did some minimal changes to this code. Look at this. This part hasn't changed pretty much anything. So I still have a map, and so now this you can look at it as a graph with the list representation. So this string represents a node, and then a node which is a list, adjacent list, and that list is going to have a bunch of pairs where there is another node and then the cost of the edge, right? So this is the graph essentially, and this for loop is going to construct the graph as we explained earlier, right? So there are no changes in this one. It's exactly the same thing. And here again, there are minimal changes, as in there is actually no change until say line number 59 or so. So we're still handling these three cases which we discussed earlier. Now, when I come down to this final case where I have both P and Q, they are not in the same list, right? We need to find a path and then find the value. That's where I'm using some kind of DFS search mechanism here. So which is not very hard here in a way. So the key vals is essentially the whole graph. And the first node of the query is the source vertex. And the second node of the query is the destination vertex. So I need to find that path and find the product of all of them. So what I'm doing here is, this is more like DFS, where when I reach a destination, I have a value, right? So once I have a value, I don't have to go through the whole graph. I can just return. So that's why I'm passing these values along the recursion. When I reach destination, I have a value, and then I can just, I don't have to go, recurse further. I just have to return back. So this is what 1.0 represents. This is the identity for multiplication to start with, right? And I need visited set, so that, in DFS, I don't have to go in cycles. So I'm going to keep track of the visited. So it is just, we just need to know whether we have visited that vertex or not. That's why I'm using a simple unordered set with that. So when I initialize, I think all of them are going to be set. All of them are going to set to false, and then I'm going to go through this. So look at DFS. It is much such a simple mechanism here. It pretty much fits into the template of DFS algorithm. So what I do here is, I'm gonna, so node is my, so the current node I'm processing in the DFS. So I take the list of that, the adjacency list of that node, which is what I call as, node map. And if the destination is present in that, that means we have reached the destination, or maybe we are at the last level. So we don't have to go one more level. We can say that we found it. So whatever the value we have got from our parent, I'm going to multiply that with the edge cost, the next edge cost, and I'm going to return, right? So I'm just returning early. I could have waited for one more level and go to that actual destination. If node becomes destination, then return maybe minus just one or val. So I could have done that, but I just did it one step earlier here. So this is about the base case, but look at the traversal. I'm going to mark this visited set for that node. And then once I set that, for each of the neighbor nodes of the node, I'm going to process. So for each neighbor, I'm processing here. If the neighbor is not yet visited, so this ensures that it is not yet visited, I'm going to visit it. So I'm going to call this DFS. So I pass pretty much everything same, just that the current node is going to be the neighbor here, right? Because neighbor is more like a pair in this case. The first one is the node value or node key, and the second one is going to be that edge cost. So I'm multiplying the edge cost to val and then passing it down the recursion, right? So otherwise there are no changes. So here line number 13 is doing the trick of, stopping the recursion early on. If I get a value which is greater than 0, that means if you don't have destination in that path, I'm going to return -1. But if there is a destination, then we get something other than -1. Because all of them are non-negative, we're going to get something greater than or equal to 0. So if I get a value, I don't have to go further. I'm going to return that one here directly. I'm not even going to explore other neighbors, right? So if none of the neighbors are have any possible value, I'm going to return -1 otherwise. So here what happens is, at any point you get a non -1 value, you are going to abort that recursive thing and then keep returning, right? That's why it's going to return quickly whenever it finds the answer, right? Even if the graph is large, once it finds the answer, it's going to stop, right? Maybe we could have used BFS to make sure if it is nearby, it runs faster and all, but DFS is much simpler. I just coded it and it works nicely, right? So this worked perfectly, and yeah, and it works, right? Let me quickly submit this code and see, and just show that it works nicely. Okay, I think I made some changes in some line while explaining. I don't know why I inserted something like this. Okay. Did it still work or not? Yeah, it is working now. This compilation error should have been gone. Let me submit that. Yeah, it is accepted. If you see the results, I think this is pretty fast, right? it took 0 milliseconds, so it's a pretty fast method, right? Probably this is the best method for this algorithm. Right? Yeah. So hopefully you understood the idea. If you need more clarity, or if you have some other solution and you want to discuss, please share it with me in the comments. Otherwise, happy coding. Keep coding at least one problem a day to keep yourself healthy.